Welcome back. In this video, what we're going to do is we're going to look at the electric field produced at the origin. But what we're going to do in this case is we're going to have a charge density that is not uniform. Okay, in the last video, what we looked at was when we had a charge density that was uniform, meaning that it didn't depend on what position you were on the rod. But in this case, you can clearly see that it does. Okay, lambda in this case is 1/9 e to the negative theta nanocoulombs per meter. So what this literally means is as the value of lambda increases, the charge density drops. Okay, so in this case, notice that the maximum value of theta is going to be pi over 2 radians. Okay, the minimum value of theta is going to be negative pi over 2 radians. And my question to you is, at what point is the charge density going to be the highest? Well, since the function inside of the exponential function is negative, that means that at negative pi over 2, this is where the charge density is going to be the highest. And so what we're going to have to do is we're going to have to calculate the net electric field at the center. But here is the problem in a problem like this. Okay, in the last one we did, the charge was uniform throughout. So what ended up happening is the y components all canceled out. But it's not going to be as nice here because the y components won't all cancel out. We're actually going to have to do two separate calculations, one for the total electric field in the x direction and one for the electric field in the y direction. Okay, so it's not going to be as nice, and then once we get those magnitudes, we're going to use the Pythagorean theorem to figure out the direction and the magnitude of the net electric field. So we're actually going to have to do two calculations here. Well, the first, I'm not going to go into the rigorous, proofs of everything, how everything works. I'm just going to do pretty straight, hardcore mathematics here, and I'm going to assume that you've already watched the previous video. So first, let me get my lambda in terms of coulombs per meter. So this is going to be equal to 1/9 times 10 to the minus 9th e to the negative theta coulombs per meter. For obvious reasons, for the rest of the video, I'm going to leave off units, but note on a test you definitely want to put those. Okay? And what we essentially found was that if I want to compute ds was essentially equal to r d theta, and my dq was equal to lambda ds, which is equal to lambda r d theta. So if I want to get an expression for dq, that becomes, well, lambda is 1/9 times 10 to the minus 9th e to the negative theta, and then I'm going to multiply that times r. I'm going to assume that the radius is 1, so let's say that the radius is 1 meter. That's multiplied by 1 times d theta. Now I'm going to solve for my differential electric field element in the x direction. So that's equal to the differential electric field total times the cosine of theta. And we know that the differential electric field element is equal to k times dq over r squared, and that's multiplied times cosine of theta. But we actually found an expression. We found an expression for dq. We found an expression for dq. So we say that k times dq, which is lambda, times r times d theta divided by r squared. And then, so this business in here that I'm putting in parentheses, that's the dq, and then that's multiplied times cosine of theta. But we actually found, and notice that this r cancels with 1 on the bottom. So if we were to write this out, we get that the differential electric field element in the x direction is equal to k times lambda, but lambda, we said lambda, let's just leave it as lambda for now. We'll expand that in a minute. But it's lambda over r, and then that's multiplied times cosine of theta d theta. If we expand out lambda, we get not k is 9 times 10 to the 9th Newton meter squared per coulomb squared. Lambda is 1/9 times 10 to the minus 9th, and then that's multiplied times e to the negative theta. I'm going to sort of take out the e to the negative theta, and then that's going to be divided by r. We said r was just 1 meter, so divided by 1, and then this is multiplied times cosine of theta d theta. Okay, and you're going to be really thankful on this integral that the coefficient here is just 1, because it could get really messy really quickly, and if you're up on your calculus skills, you know exactly why. Okay, so this all goes to 1, so we don't have to worry about that. So now the idea is we have to integrate both sides. So we're going to integrate the differential electric field element in the x direction from 0 to e sub x, and then all this business we're going to integrate from negative pi over 2 to positive pi over 2. So we have to do that to this over here. So this is going to be integrated from negative pi over 2 to positive pi over 2. So let's actually come down here and look at the integral itself. Okay, so we're going to evaluate the integral of e to the negative theta cosine of theta d theta. Okay, and this is going to be evaluated from, let me do this, just for simplicity so I'm not writing this over and over again, let me define pi over 2, let's call that b, and let's say negative pi over 2 is a. So in that case I can just say this is from a to b. Okay, I don't want to have to write that over and over again. So this is the integral from a to b of e to the negative theta times cosine of theta d theta. And now we have two functions inside the integrand. So this is probably a hint that we're going to use integration by parts. So we can do this any way we want, but let me do this. Let me define this integral. Let me define this integral as beta. Okay, and you'll see why I do that in a minute. So that integral, all this business right here, this is just beta. Okay, you'll see why I do that later. So that's beta. Well, now let's pick our substitutions for integration by parts. Let's let u, let's say that's equal to e to the negative theta. Okay, so that means du, if we take the derivative of this guy, we get negative e to the negative theta d theta. Okay. Our dv is therefore cosine of theta d theta, and so if we integrate that, we get v is equal to sine of theta. Okay, so let's do this. Let's say that beta, and that's 1 beta, by the way, 1 beta is equal to uv. Let's just e to the negative theta sine of theta, and then we subtract, and by the way, this is evaluated from a to b, and then we subtract off the integral from a to b of v du. So this is minus e to the negative theta d theta, and then times sine of theta. I did that right, so we have v is sine of theta, du is negative e to the negative theta d theta. Okay, so we have this. Let's clean this up a little bit. So this is equal to e to the negative theta times sine of theta, evaluated from a to b, plus the integral from a to b. And the reason I'm adding it now is because the negative cancel, and I get this is the integral of e to the negative theta sine of theta d theta. Okay, so this is my new integral. And when it's evaluated from a to b, it'll be equal to 1 beta. Okay. Now let me do another substitution, because we're going to have to do it again. You may see that we're not getting anywhere. It doesn't seem like we're getting anywhere, but we're going to have to do integration by parts a second time, and I promise you we're going to get somewhere. Let me let w is going to be equal to e to the negative theta. Okay, that's this business right there. So if we take the derivative, put it in differential notation, dw is equal to negative e to the negative theta d theta. Okay, let me scroll over a little bit. Okay, then I'll do that. Let me do this in purple. So then I'm going to have dz. dz is just going to be sine of theta d theta. So this is sine of theta d theta. What's the integral of sine of theta d theta? Well, the integral of sine of theta d theta is just negative cosine of theta. Okay, so let's use these substitutions. Okay, so let me first rewrite this first part again. So this is going to be 1 beta is equal to e to the minus theta sine of theta evaluated from a to b, plus, put this in brackets. For this one, it's not going to be u times v, it's going to be w times z, because I made the substitution with those variables. So plus w times z, well, that's just e to the minus theta times negative cosine of theta times negative cosine of theta, and that's evaluated from a to b, right? I did that right. W is e to the minus theta times z is negative cosine of theta, right? And then I subtract off the integral from a to b of z dw. Well, that's basically, if I do this right, it's going to be negative cosine of theta, right? And then multiply times negative e to the negative theta d theta, close brackets, okay? So what this is going to be is 1, and let me actually, let me just keep it like this for a minute. We'll say 1 beta is equal to e to the minus theta sine of theta from a to b. This is going to be minus e to the minus theta times cosine of theta. I just pulled the minus sign out in front and then evaluate that from a to b. Well, these minus signs essentially cancel, so it's minus the integral of e to the negative theta cosine of theta d theta. But notice I made that substitution with beta, right? The integral from a to b of e to the negative theta cosine of theta d theta is just beta. So this is minus 1 beta. And that's the reason I made this substitution. So what I can do is I can add 1 beta to both sides. So notice the plus 1 beta cancels with the minus 1 beta. And I get that 2 beta is equal to e to the minus theta times sine of theta. I'm actually going to pull the evaluation to the end. And this is going to be minus e to the minus theta times cosine of theta. And all that is evaluated from a to b. Okay? And so now what I can do is I can divide both sides by 2. And notice that beta was just the integral of e to the negative theta cosine of theta. So this is just the integral from a to b of e to the minus theta cosine of theta d theta. And we just evaluated the integral. It's basically equal to, let me just do it like this. E to the minus theta times the sine of theta over 2, evaluated from a to b, and then minus e to the minus theta cosine of theta divided by 2, evaluated from a to b. And just keep in mind, b was pi over 2 radians, a was negative pi over 2 radians. So if I factor out the evaluation, I'm going to get e to the negative theta times sine of theta minus cosine of theta over 2, and that's evaluated from a to b. So let's sort of chug through this, okay? And what I'm going to do, these numbers are not going to work out very nicely. So what I'll end up doing is I will stop the video after this and I will calculate the numbers for us. And then in the next video, we'll actually look at what it is. Okay. So what we're going to do is we're going to take e to the minus, well, the upper limit is pi over 2. So this is going to be e to the minus pi over 2 multiplied by, what's sine of pi over 2? Well, sine of pi over 2 is 1, right? And minus cosine of pi over 2. Well, cosine of pi over 2, cosine of 90 is 0. This is 0, okay? And then we subtract off from that, evaluated at the lower limit. So this is, A is negative pi over 2. So this is e to the negative, and then we evaluate theta, it's negative pi over 2 over 2, multiplied by, what's sine of negative pi over 2? Well, we're looking at the vertical component of basically at, so if we go back up to the top here, so if we look at where negative pi over 2 is, what's the vertical component there? It's minus 1. Okay, so this is times sine of negative pi over 2 is minus 1, and then we subtract from that cosine of negative pi over 2, but that's still 0. Okay, so if we simplify what the x component is here, you should get 1/2, I'm factoring out the 1/2, times, well, actually, let me not do it. Let me not factor out the 1/2. Let's just do it like this. We have e to the negative pi over 2 times 1. Well, this minus sign will cancel with this one. So then I'm going to get plus, these minus signs will cancel, and it's going to be e to the pi over 2 divided by 2. And this right here, this is the electric field in the x direction. And so what I've done is I actually made the decision that I actually went and paused the video, and I went and actually calculated what this turns out to be. And it turns out that the electric field in the x direction for this charge distribution of the rod is equal to approximately 2.51 newtons per coulomb. Okay? So that's only for the x direction. Now notice that in this case, we don't have a uniform charge distribution, right? It's not uniform. So that implies that the y component is not necessarily going to cancel out, okay? The y component will not cancel out. Well, there's not going to be a whole lot that changes in our expression. What's essentially going to change is the expression for dE sub y. Okay, it's going to be similar, but not the same. So notice that with respect to theta here, the y component, and we could go above the x-axis too, but the y component in any case is going to be the opposite side with respect to theta, about the hypotenuse. So if we were to obtain an expression, so we know that lambda is irrespective of the x and y coordinates. It's just equal to 1/9 times 10 to the minus 9th e to the negative theta. So notice, lambda does not depend on x and y. It only depends on theta. We know that dq is equal to lambda r d theta. And what we can write is something a little bit different than we did in the last problem. We can say that the differential electric field element in the y direction is equal to the differential electric field element total times the sine of theta. So notice it is different. We're talking about the sine of theta now, because keep in mind we're dealing with the opposite side of theta. Okay? So we know this. We also know that for any differential electric field element, it's equal to k times dq over r squared. So let's set up the differential. We can say that the differential element of the electric field in the y direction is equal to k times dq, right, over r squared. That basically says the electric field total, but we want that multiplied times the sine of theta multiplied by the sine of theta. Okay, let's expand this out. We have k. We know the expression for dq, that's lambda times r times d theta over r squared, and that's multiplied times the sine of theta. And then we know that lambda, let's actually start plugging in numbers. First of all, notice that 1r cancels with 1 on the bottom. K is 9 times 10 to the 9th Newton meters squared per Coulomb squared. Lambda is 1/9 times 10 to the minus 9th, and we have this times e to the minus theta. This will be multiplied times sine of theta d theta, and then you have an r on the bottom, but we said r was 1 meter. So all this business that's right here cancels to 1. 10 to the 9th times 10 to the minus 9th is 1. 9 divided by 9 is 1. So literally when we do this integral, we would say that the electric field in the y direction is basically equal to the integral of e to the negative theta sine of theta d theta, but because it's the same circle, we have the same limits of integration. So I'm going to stick to using a and b just for simplicity. And basically the same thing is going to happen here as we did in the last problem. So let's write this again. We have the integral from a to b, which is negative pi over 2 to positive pi over 2, of e to the minus theta sine of theta d theta. I'm going to define this one as alpha. I just picked a random Greek letter, but I'm going to define this as alpha, and let's make some substitutions. Let's say, what letters? Let's say I is equal to e to the minus theta, so di is equal to negative e to the minus theta d theta. So let's say dj is equal to sine of theta d theta. So this is sine of theta d theta. What's the integral of sine of theta d theta for j? Well, it's negative cosine of theta. And take the differential of j equals negative cosine of theta. You should get sine of theta d theta. Okay, so I'm going to say that this is 1 alpha, and it equals I times j, which is negative e to the minus theta times cosine of theta. That's, of course, evaluated from a to b. And then you're going to subtract off from that the integral from a to b of j di. So this is negative cosine of theta multiplied times negative e to the negative theta d theta. Okay? And so if you simplify this a little bit, you get negative e to the minus theta cosine of theta from a to b. These minus signs cancel, and so you get minus the integral from a to b of e to the minus theta cosine of theta times d theta. Okay? So this is your new integral, and that's, of course, equal to 1 alpha, where alpha is this guy over here. Let's do another substitution. We got to pick new letters. Let's pick p. We'll say p for this one's equal to e to the minus theta. So dp is equal to, let me erase that, dp is equal to negative e to the minus theta d theta. Okay? Let's pick dq. Actually, that's not a good one. We don't put dq. Let's say dn. I don't want to use dq because that was our charge distribution. So dn is equal to, in this case, cosine of theta d theta. So that means n is equal to sine of theta. Okay? So now what we'll do is we will keep on going with this integral. So we know 1 alpha is equal to negative e to the minus theta cosine of theta from a to b minus, so we have to make sure to put this all in brackets so that we distribute the minus sign. It's the integral of e to the theta times e to the negative theta times cosine of theta d theta. We made these substitutions. It's going to be p times n. We're distributing this negative sign, so this is e to the minus theta times sine of theta. That's evaluated from a to b. And we have to make sure to subtract this integral. And this integral is going to be n dp. So it's going to be integral of e to the minus, negative e to the minus theta, right, times d theta, and then times sine of theta. Make sure, did they write sine of theta times negative e to the minus theta d theta, evaluated from a to b. Notice that these negative signs cancel to give you a positive. Okay, let's rewrite this a little bit. We have 1 alpha is equal to negative e to the minus theta cosine of theta from a to b minus e to the minus theta sine of theta evaluated from a to b. And then we subtract from that the integral from a to b of e to the minus theta sine of theta d theta, but that was alpha. We made that substitution right here. So this is minus 1 alpha. We can add 1 alpha to both sides of the equation, and we end up with 2 alpha is equal to negative e to the minus theta times cosine of theta evaluated from a to b minus e to the minus theta times sine of theta evaluated from a to b. The 1 alpha and minus 1 alpha cancel. We can divide both sides here by 2, put this in brackets, and divide both sides by 2. But remember that the alpha was equal to the integral from a to b, make sure I do this right, e to the minus theta sine of theta d theta. That's equal to, so it's going to be, let's factor out a minus 1/2. So we factor out a minus 1/2, because here's the times 1/2. There's a negative sign in both cases. This becomes e to the minus theta times cosine of theta from a to b. Well, if I factor out a minus sign, then this becomes plus e to the minus theta times sine of theta. Oops, and that's evaluated from a to b. Okay. And then what I can do is I can simplify this a little bit more. I can say that we have negative 1/2 multiplied by, let me factor out an e to the minus theta. So this is e to the minus theta times, this will be cosine of theta plus sine of theta, and everything is evaluated. I'm going to substitute the a and b back in here. This is negative pi over 2 to positive pi over 2. Okay? So now what I'll do is I'll go ahead and evaluate this, start plugging in some numbers. This is going to be equal to negative 1/2 times, well, the first thing we're going to do is evaluate this at pi over 2. So this will be e to the negative pi over 2, and it's times cosine of pi over 2 plus sine of pi over 2. Well, what's cosine of pi over 2? If you're looking at the unit circle, pi over 2 is 90 degrees, and so the horizontal component of that is 0. But sine of pi over 2 is 1, so this is 0 plus 1. So it's basically negative 1/2 times e to the negative pi over 2. And then you subtract off from that the other evaluations. This is minus negative 1/2 times, well, now you're going to evaluate this at negative pi over 2. So this is e to the minus pi over 2. And that's multiplied times cosine of negative pi over 2 is still 0, plus sine of negative pi over 2, that's 0, and then minus 1. So let's simplify this as much as we can. The first term is just e to the minus pi over 2, or negative e to the minus pi over 2, because you'll end up getting 0 plus 1 is 1, times e to the negative pi over 2, which is e to the negative pi over 2, times negative 1/2 is this. Okay, notice here, these minus signs cancel, so you should get an e to the positive pi over 2. Notice that, let's see what happens. Well, let's keep going. So it's going to be, this minus sign will cancel with this, so it'll be plus 1/2 times e to the pi over 2, and then you're multiplying by negative 1. So this is equal to let's see, negative e to the negative pi over 2 all divided by 2, and then minus e to the pi over 2, see, minus, over 2. We can factor some stuff out. Let's factor out, we have minus 1/2 we can factor out. And this is multiplied times, we have e to the minus pi over 2. If we factor out the minus 1/2, this becomes plus e to the pi over 2. Well, let's make sure we did that. Let's distribute it to make sure we did it right. So we should have negative e to the negative pi over 2 over 2 and minus e to the pi over 2 over 2. So this is right. I'm going to pause the video and calculate what this is. So I've calculated what this is, and it turns out that it's the electric field. By the way, this is the electric field in the y direction is approximately negative 2.51 newtons per coulomb. Okay, so now we know the electric field contributed by the y component. What was the electric field component that we calculated for the x direction? Well, let's go back over here. And the electric field for the x direction, it looks like, is also the same magnitude, 2.51 newtons per coulomb. And notice what ended up happening when it got spit out of the integral. The electric field that was in the x direction was 2.51 newtons per coulomb. So it's the same magnitude, but the opposite direction. Now, these problems where you're dealing with a ring of curvature, they can get really tricky. Let me show you why. Okay, so these are the two components. So if we come back over here, I copied and pasted this picture right here, if I can find it somewhere. Here it is up at the top. Okay, so here's our original picture. So you have to be a little bit careful whenever you're looking at the direction of the electric field for this system. Okay, keep in mind that when we integrated from negative pi over 2 to pi over 2, okay, we were essentially integrating in this direction from here to here. So in other words, we're integrating over theta values that are on the right side of the y-axis. And if this angle right here is theta, then by alternate interior angles, this has to be theta as well. Okay, so notice that the theta that's used to define the vector is on the opposite side of the x-axis as the theta that was used in the integration. So this value of y, let me find it, the value of y that we obtained through the integration, the sign needs to be flipped. And the reason is because the theta over which we evaluated the integral was on the opposite side of the x-axis. So we basically here need to flip the sign for this one. Okay? Now here's another question. If you think about it, for the x value, we got a positive electric field. But that, oops, let me erase that. That simply can't be the case. Because if we go back to our picture once again, we know that electric field lines, they should point away from positive charge. And, the electric field calculation that we got through the x-axis, or the x direction integral, says it should go to the right. But that can't be the case. But we also have to realize that for the x vector, we actually physically defined this right here. We defined it as going in the negative direction. Okay? So the differential x component of the electric field is in the x direction. So because we got a positive value, once again, we have to flip the sign of it. Okay? So if we come back here, not only do we have to flip the sign for the y one, but we also have to flip the sign for the x one, okay, as well. Okay, so what we'll do now is we'll sort of draw a picture to determine the direction of the electric field. So let's consider this. Let's rewrite this as the electric field in the y component. We flip the sign is going to be positive 2.51 newtons per coulomb. In the x direction, it should be negative 2.51 newtons per coulomb. Okay. Let's see. Okay, now we're going to draw a picture. So let's say that this is our origin, the place we're evaluating the integral at. And in the x direction, we're going to displace negative 2.51 newtons per coulomb. That's the vector that goes in the x direction, and in the y direction it's going to go the same magnitude up at positive 2.51 newtons per coulomb. And what we're going to do is we're going to do vector addition, but we really don't need to compute a direction because both vector lengths are exactly the same, so it should be pretty obvious that this theta right here equals this theta right there. If you were to express it in degrees, theta would be 45 degrees, but theta really in terms of radians is pi over 4 radians. And what we would say in terms of the direction is it is, we'll say, pi over 4 radians clockwise from the negative x-axis. So we'll say it's pi over 4 radians clockwise because we're going to move this direction, right? It's clockwise from the negative x-axis. So that's the direction. And to calculate the magnitude of the electric field, what we're going to do is we're going to say E total is going to be equal to the square root of, we'll take this squared. Notice that the x direction, it's negative 2.51 newtons per coulomb, so negative 2.51 squared plus the square of the y component, which is 2.51 newtons per coulomb. We square that, and we take the square root, and it turns out that the total electric field felt at the origin is approximately 3.55 newtons per coulomb. So what did we have to do to get that? We had to do a lot of work, integration by parts. For that matter, it's really complicated integration by parts. But really, let's see if this direction actually makes sense. Let's see if it makes sense. So we're saying that the electric field is strongest. Basically, if this is quadrant 1, it's strongest in quadrant 2, right? So let's think about why that would be the case. Okay. Well, if we look at our picture, right, if we go back to what our lambda was equal to 1/9 times 10 to the minus 9th. We really don't care about this constant out in front, but it's essentially e to the minus theta, and that was in units of coulombs per meter. If we look at the graph of e to the minus theta, what will that look like? Well, the graph of e to the minus theta, if our x-axis is theta, and the y-axis is the value of our exponential function, all the thetas will be the negative. So it'll essentially look like this. It'll look like something like that, right? So all the theta values are flipped. So in other words, and by the way, this would essentially be where it crosses the y-axis at 1, 0. So the question is this: what values of theta will produce the highest charge per meter, right? So in other words, what values would I plug into this theta for the value of lambda to rise, right? Because what we know is that lambda is directly proportional to the charge, and the charge is directly proportional to the electric field. So wherever lambda is highest, that should be what produces the strongest electric field, okay? Well, what value of theta would produce the highest lambda? Well, it's going to be negative pi over 2. Well, where is your electric field going to be greatest? Well, like we said, it's going to be greatest wherever lambda is greatest, because electric field is proportional to the charge, and charge is proportional to lambda. Well, where is lambda greatest? Well, you're taking e to the negative theta, so whatever has the highest negativity of theta is going to have the highest lambda. And it turns out that that's negative pi over 2. So that means the electric field vectors that are produced at the origin, they're going to be highest radiating from pi over 2, and they're going to decrease as you go towards pi over 2. Now, they're not going to decay to 0 because e to the negative pi over 2 is not 0. So literally what they would look like is something like this. So let's sort of draw a picture. So here is your, this isn't very good, but let's say this is your origin. So what the electric field vectors would look like is this. So if you think about it, the electric field vector should be strongest coming from negative pi over 2. So what will happen is you'll have a strong vector that goes like this, and I'm just going to draw a few of them. And then you're going to have a weaker one that goes right here, and they're sort of going to get weaker and weaker as you rotate around until finally you get to this point. So basically, this vector comes from negative pi over 2. This small one comes from pi over 2. So as you're rotating around, starting at negative pi over 2, the electric field vector should be the longest, because stronger electric fields means longer vectors. So the vector should be the longest there, and they should decay as you integrate up to pi over 2. At least that's how it should be, both in the x and y directions. Okay, and in fact, that's actually why the magnitudes came out exactly the same. Okay, so I hope this video gave you a little bit of intuition on how to go about doing these problems. This is a really complicated one. See you in the next video.